31. Warten noch ein paar Minuten. Okay, 8:55. Welcome to our next Distributed Information Systems lecture. Today's topic will be mostly something, a small session about optimization when you use sockets. Then we talk shortly about what the use of protocols in general, and then we will take a more in-depth look at threading and synchronization, and that will presumably take us take up all the rest of the time, but we will see. So no one has yet entered, so let's take a look at the new exercise sheet version, because during yesterday's holiday I was able to generate the new exercise. Just maximize this screen, then share the other one. So, of course, everything gets small again, and we don't want that. So, as you can see, this is the first exercise sheet we already know. And what I did was to extend it slightly. The problem is this, of course, also has some aspects regarding the client commands, which is not something you have to do. This is something I integrated during the previous exercises for the next classes, for the next years. But if you want to make your system more flexible, then of course you can support that as well. But it is not necessarily needed to get the 5%. Typically, I update the exercises on a yearly basis due to, okay, what was running well and what wasn't running well. And therefore, this has been integrated because it seems useful from my perspective, especially that you see what happens when the server shuts down the client or closes the socket to the client. If the client closes the socket to the server, and being able to shut down the server as a whole. And when the server is shut down in a graceful manner, then the port isn't blocked anymore, and you can restart the server without changing the port or without killing anything in the background, without waiting. In order to do something like that, of course, you need to communicate with the system, and therefore I integrated these 3 commands that should be the next year should support quit when the client closes the socket itself, its own socket part, and shuts down drop when the server should drop the client connection, and then the client realizes or doesn't realize that something bad has happened, and the shutdown command also. But you can or cannot support that. In addition, something that might be of use for today, what you all need to be or what you all have finished with today is definitely task 1.2a, because we need that. 1.2b and 1.2c is something that is of lesser importance. So if you are trailing somewhat behind, try not to do 1.2b and 1.2c first of all, but try 1.2d, A, B, C, D, yeah, D. And because that is more relevant, being able to support multiple clients is a more relevant thing than being able to communicate via UDP or switching to IP version 6. So this has a higher priority from a learning perspective than these two. Of course, if you already played around with sockets, then you should try out everything. And if you still have time, try to solve UDP and TCP as well. But today, everyone should be capable of solving 1.2a. That's definitely a thing. If you trail that too much behind, then everything else will go on top. As you can see, 1.2e is the bonus question, and I split it up, namely the idea, which is we have a shared resource that is managed by the socket server, but I will not go through everything because it's quite lengthy, because it's quite complicated. And therefore, if you want to get the bonus points, bonus percentages, you just contact me. And if you have questions regarding the content, and then we talk things through. But typically, this exercise takes up lots of time, and especially if you are not have already programmed sockets, then don't try to go for the bonus points. This will take some time. The bonus points are split up into 2 parts, part A and part B. Part A is you manage a queue of jobs, and the access to the queue is critical, and you have to synchronize that. And when no job is available, the threading mechanism that is inside this shared resource should sleep for a second, then check the queue again. If nothing is in there, sleep for a second, check the queue again. So it's always active in the background, which is of course not something you want, but it's a simple approach. And therefore this is a so-called polling approach. The thing is trying polling in the background, checking all the time. And of course 1.2e part B is the more sophisticated, because it uses semaphore signals or mutexes or whatever you come up with to actively block the thread from checking the queue and unblocking the process when a new job is entered into the queue. And as you can see, multiple things are necessary. So these are the structures and methods and stuff like that that you need to solve that. And depending on what your solution is, it may be more or less, but it's a bonus question. And therefore, so today's idea is definitely getting 1.2a done and work on 1.2d if possible, because after 1.2d, then we get to the point where we build the system in a way that we can later use it for the overall exercise goal. So everything else was just preparation until 1.3a. Getting the system up and running, setting up the communication, being able to communicate between client and server. And with 1.3, we start to integrate a so-called protocol that we can then use between client and server for the client to tell the server what it wants, and the client and the server being able to understand what the client wants from it. So that's the first thing, and we start implementing this kind of protocol, which is very simple, but for our exercise, it's sufficient. We start again on the C++ side, being able to communicate the protocol from the C++ client to the C++ server, and the server analyzes the question, generates the answer, sends it back to the client, and everything is fine and happy. And when this works, we start with the Java client, being able to set up a Java socket client, communicating with the with the C++ socket server. And when these two are able to communicate, then we put an API on top of that, so an interface that hides the communication that takes place in the background. And the Java client, when I call a method of the Java client that implements this interface, in the background, the socket communication is initiated. The matching protocol for this command is constructed, sent via socket to the server. The server generates the answer, sends it back over the socket to the Java implementation of this interface, and the Java implementation of this interface restructures what the server sent and provides it in a decent manner that this interface wants. And that's basically the idea. And then this interface implementation object will later go into our dynamic web client or web server in our servlet that generates dynamic web pages, and then things start to getting interesting, and that's basically the idea.
So the question was rising yesterday with some students of automotive computing. Since the guideline is to show the lecturer the finished or more or less finished version of the exercise before the start of the next exercise.
Yeah.
And when I look at the deadline, it's next Monday. We also have Verteilte Informationssysteme. So I didn't get, when do we really finish? We do have to make up a meeting where every team shows you or Plattner. That's the first question. The functionality, or is it already always made in the lectures, in the Übungen?
It will be in the exercises. So in the exercises, when you think, okay, I finished my exercises, this is how far I did get, I will start with the new exercise sheet. You contact me via chat, just if the same procedure as if you have a question, I have a problem, can you help me? And this time you write, okay, I want to show my exercise 1. And then I will contact you. Both of the team goes together with me in a private chat. And then we go through every single exercise that is available in the exercise sheet. And I ask you, have you solved this one? Have you solved this one? Show it to me. And then you show me that you did solve this exercise by proving that it works. And then I make a mark on my list saying, okay, group whoever has solved A, B, C from 1.1, and from 1.2, B, D, and E, and from 1.3, C and D. And then the percentages are accumulated, and that will be your overall percentage.
Okay, so it's not with Plattner because we have the exercise with Plattner, so it's definitely with you?
Yeah, that's the problem, because you have Michael. Yeah, that's not a problem. You check in with Michael.
Okay, just to know.
You contact Michael, and tell him you want to show him your exercise, and I will send him this evaluation sheet, and he will just fill it out and
Okay, because he already does this sort of checking when we start the exercise. He gets into the groups, asks how far are you? Can you show me some things? That's why I was not sure if it was already in place, this method now, or if it is not that official, which we do have to do. But since we have to show it at least before the next exercise, what's is on Monday the next exercise? Also should we do we begin with the next exercise sheet on Monday, or?
No, it will be on Wednesday. I think we have another one, Wednesday or Thursday. I don't know. Let's check what's next week's schedule. Yeah, Wednesday. So deadline is on Monday midnight, somewhere around midnight, I presume.
Okay, so then we should upload it, but then we have still time to
show it on Wednesday. Exactly.
On Wednesday. Okay, got it.
And if multiple people don't have enough time to work on that, we can discuss if we can extend the thing.
Mm-hmm. Okay.
But I need the input and not at midnight.
No, it's clear. It's clear. I just wanted to clear that out. What's the Abgabe date and the presentation date difference, or start on Monday with it? Okay.
Yeah, so you upload till midnight, 5 minutes till midnight on Monday, and you can show me your results on Wednesday then.
Okay.
So on your side, you show it to Mr. Plattner.
The plan is to show the exercise always after the due date. Is it right?
Yeah.
Okay.
Or if you finished early, you can definitely do it before the due date. You don't need to target the due date perfectly. It's a deadline. You can finish earlier. I know that's a surprise, but it's definitely good to finish earlier. And then, of course, you can show me as soon as you finished your exercise and say, okay, this will be the version I upload, or I will upload, or we will upload. Then you can show me your results, and then I make my marks in this list. And you can show it to Mr. Plattner, or he checks during your exercise by switching groups. Completely in your hands.
But the upload an sich is just to upload it, but the real grading is in the presentation. Or?
Not completely. So the functionality grading is in the presentation. So I will check what functionality your system provides. But regarding the documentation style guides and dubious programming styles and naming conventions and stuff like that, they are checked afterwards based on what you uploaded.
Okay.
Okay, any more questions regarding that?
Just so, like when we show it to you, the only thing we have to do is like start the program and go through A to D with everything. Okay.
In principle, I will ask you, show me this, show me that, or what have you done? What didn't you do? So I will make a minuses or what you didn't do, and then we check what you think you did solve. And for instance, when we check, so I will not typically, depends if you have done nearly nothing, of course I have to check that, but A, B, C will not be checked. If you have something like this, if you have a class that is capable of starting a server and a client and they are both able to communicate, I assume that you successfully solved A, B, and C. So I will not check every single aspect. I will check the big chunks, and if the big chunks work, you get the points for the small chunks as well, if they are associated to this branch of exercise. But for instance, this UDP stuff and the TCP stuff, version 6, this is something I need to check by you setting up the server, showing me the code. Okay, there I can see that you use the IP version 6. address struct and stuff like that. Same goes with UDP. You show me where you send the data. You show me that you can send data to a server and reply to the associated client. And then I tell you, okay, show me in code, and you go open up the UDP server, show me, okay, here you can see send to, and here you can see receive from. The same on the client side, and then I say, okay, you did it, points achieved. And that's basically it. But A, B, C, this warm-up stuff, I typically don't check, because if you're capable of doing a class that is representing an echo server, you of course can connect to a server and can reply, and the client can reply to the server and stuff like that. Okay.
All right.
Perfect. Any more questions regarding that?
Only one. Only the TCP for version 6. Only the one TCP server has to support version 6.
Yeah, exactly. Because it's not something that is of high interest to support version 6. It's just something you need to know and work with at some point in time.
Thanks.
Okay. Any more questions? You're wasting precious time. I have so many slides I need to show you. We still have to do the break, I was told. So if there are no questions regarding the exercise, be aware, B and C are less priority than D. So if you finished with A during the day, don't go to B and C, go straight to D, okay? This is more important because the learning curve is more important with the threading than with the UDP and TCP version 6. Okay, having said that, let's move to the content. So give me a second. So socket optimization was where we left last time we met. So socket optimization is, optimization is slightly exaggerating, but there are some things you need to take care of. As I told you, there are books with multiple hundred pages that are just about socket optimization and how sockets work and where you can tweak it. And this is way over the timetable or time scale we have in this lecture. So socket optimization is a huge topic. But the most of us, 99% of us, will never touch a socket on that level of abstraction level. So you typically use just the REST service and be happy with it. But in the background, of course, sockets are doing the job and you could play around with them. One thing that you can integrate later on is you can manipulate the socket options. So as I told you, there are many ways to manipulate the socket internally, the socket layer, the communication layer that is doing this organization in the background. And in order to set some options for the socket layer, you have to use the sock-opt method. And again, this is a Microsoft version of this because yes, you can see the socket type, and as you know, in the Linux world, we use just an integer, but the same thing exists for the Linux and iOS world. And we can manipulate the options of the socket. We can manipulate the options on different levels. We can manipulate the socket layer itself. We can manipulate the TCP layer, and we can manipulate the IP layer. Try to remember this ISO-OSI model, which you definitely have talked about in some other lectures, and we take a look at it later on as well. So we can manipulate different layers of this ISO-OSI communication model. And one option you could try to manipulate is the socket option reuse address. which on some systems solve this the port is blocked problem, but only on some systems. I think the Windows, if you do solve this with the Visual Studio, then this might help you. For all the rest of us, this will not work. So if you're using Cygwin version, then and C-Line, this will solve. This will not help you out. The only thing that keeps the port from blocking is shutting down the server gracefully. And then, of course, you need to have a client that sends the command shut down to the server, and you need to interpret that. And then the server shuts down, closes the socket handles, and then you can restart the server with a blink of an eye. Nevertheless, there are some systems that support this reuse address, and then you can work with that. Which brings us to what parameters are provided, the socket, which level of this communication block are you targeting? So socket layer, TCP layer, IP layer. What option are you referencing? What value do you want to set? And what's the size of this type you're providing? And of course, there's always a return value, or not always, but in this case, there is a return value. And if it's -1, then something didn't go well and you have not set the socket options, even if you called the method. One thing that needs to be taken into account is that this set socket options should be called after the bind call, and not before the bind call, and not after the listen call. It's between bind and listen. And this is the implementation, or this is how an implementation could look like. And you can integrate that or not. Then some typical problems that arise when we talk, when we use sockets. Of course, in our exercise, we make sure that everything can be communicated in one go, in one swift communication try. And you all know that when we really want to transfer some big data, much data, then this sending data will not sufficiently or successfully communicate all the data at once. So this is the problem we talked about last time. If we have more data to send than we can send in one try, then of course you have to check the return values and chunk the data and then communicate the data piece by piece by piece until everything has been communicated to your communication partner.
There's a question rising in the exercise with Plattner, which we didn't probably discuss. We get it that when we use the send command and the sended amount of bytes is not the size which we send, that we had a split in there, but the receiver can't know. Or do we say
something I already talked about last time? This problem is solved by supporting a protocol. So as you said, the receiver cannot know that it was split up, but if you use a protocol that tells you, okay, this is protocol X and the command I send you ends until a special sign is received, and the special sign is not in the block you received, then another block needs to be attached to the command.
Okay.
Or you have something like an HTTP where you tell, okay, we have some headers and then comes the content, and before the content is provided, you provide the number of bytes representing the content size. And then of course you know, okay, there will be 3 gigabytes of data. And then you know, okay, 3 gigabytes of data, I cannot store that in one go, so I have to do it multiple times. That totally depends on the protocol. Okay? And as this makes your life even more complicated than it is already, we don't have this problem in the exercise. I had degree years where we had that problem because I restricted the size you could grab out of a socket to 1 byte. And of course, then you need to try this reading multiple times because you only get 1 byte of the socket. But of course, this was just as we had more time. So, and as it is stated, how does the server, in this case the receiver, know that a complete command has been received? Based on a use protocol that defines the length of the message or uses terminal symbols. So this is exactly what you were questioning, again, written down on this slide. And I explained it before. Okay. So this is how it is typically solved, this problem. Detecting a communication abort, this is something I told you at least a dozen times in this lecture alone. If there is a return value, you have to use it, check it, and if something goes wrong, depending on what part of this, whatever you are trying to do goes wrong, and if it's severe, you don't need to continue. So even last week when we, in the exercise, I was asked by quite a lot of people having problems with their socket communication. And the reason was they didn't check the return values and the bind command has failed and they try to go to the accept command. And of course, if the bind fails, you don't need to try to accept. It's already done. It's lost. So check the return values, and it's the only way to detect the problem. Otherwise, it's just tapping in the dark. On the receiving side, 3 possibilities. On the sending side, 2 possibilities. So that needs to be taken into account, and you definitely have to check that. And if you don't do that and upload your solution, I will definitely reduce your percentages on the dubious programming style. Something that you can use when you have a large chunk of data and you know you have typically large chunks of data to communicate between client and server. You can try to optimize the splitting up of the huge data into tiny chunks, because when you split up the data, you have to decide, okay, how big should the chunks be? And the chunks be in an optimal situation should be the maximum of the message, maximum segment size message. So the maximum that goes through a socket communication in one step. And in order to find out how big that is, you can fine-tune the size of your communication buffer. So the idea is now we send something with a buffer size, and we can optimize this buffer size to the buffer size is as big as possible without being split up internally by the socket itself. So you split up your data package due to whatever you think is right, and the socket internally also tries to split up bigger packages into smaller packages. And of course, it would be perfect and optimized if the size you put into the socket is the same size as the socket uses internally. Then there is no need to split up anything again. So this optimizes it. And the idea is to find out the maximum segment size, which is the maximum size of the payload inside this media maximum transmission unit. But this is typically only useful when you know you are communicating large pieces of data over a fixed communication line. And this is just for information reasons. What you also can do is try to manipulate the internally used socket buffer. So you put in your chunk of data, and the socket, of course, has a buffering mechanism inside, accumulating data, then splitting up the data and communicating the data to its counterpart. And you can, of course, manipulate this receive and send buffer that is used internally inside the socket layer by manipulating the socket options. And The general buffer size is around 8 KB, and you can upgrade that or downgrade that depending on what you want to achieve. But of course, this has no influence upon this. And this is influenced by which routers, which way the communication is handled. So you can have larger pieces in your internal network structure, then the package goes outside into some other network, into a network part that is not managed by you. And then suddenly the size can be reduced and this thing is split up again. And so this depends on if you want to only communicate internally or also externally. And if you're trying to do that externally, of course, the amount of work you need to put into that is increased. Okay, so what are also aspects you need to take into account? It's useful to write fewer bigger chunks of data than many small packages, because with every communication, of course, the socket adds its header information and its trailing information. So you lose useful bandwidth. When you only need to send small packages, then you might try to optimize or to accelerate the communication by setting this TCP no delay socket option. Because internally, in the background, with this 8 KB buffer, which we talked about here, the socket tries to not send many small packages. So you put data into the socket, and then the socket realizes, okay, this is just 2 bytes. Why should I send that? Let's wait a little bit. Perhaps there's more data to be sent. And therefore, the socket internally actively waits a little bit in order to get more data to fill up this maximum segment size to a better proportion. And of course, you can deactivate this so-called Nagel algorithm, and then the socket will not try something like that and communicates whatever you want in one swift go. But that's something also in the background. And as I said, if you're just using REST APIs and some other fancy stuff, of course, then you're way too up in the ISO-OSI layer to manipulate that in any way. But if you're really down in the cellar and need to manipulate something and optimize something, this may be something. What you can also use is splitting up control and data communication channels, like it's done with FTP. So you can set up a socket that just sends control information, and you set up another socket that is responsible for the data communication, or multiple sockets for the data communication. So you can send data in multiple channels and hope that it accelerates your communication style. So multiple sockets to send data. And of course, if you're quite confident that the network is capable of handling that, and if the packages are not so important that they need to arrive in correct order, and it's not, if a package can be dropped at some point, then you can of course use UDP instead of TCP, which is way faster, because it has less overhead and does not do any error correction at all. And this, of course, is something that is transparent to us, hidden to us, and is done by the TCP, by this communication layer. And if we want to get rid of that, we just use UDP sockets, and then things go in a swifter way. What are the typical error sources I tend to see? As I already stated, you ignore the return values, which is a bad thing if you don't know what you're doing, or if you're doing it the first time, you should take a look at the return values. Ignore the termination of the communication. You're trying to ride a dead horse. It is already done, and of course this won't work. which is typically a side effect of return, ignoring the return values, ignoring the endian problem, so not using this N to host to network short and network to host short thingy. The problems based on address already in use. We talked about possibilities solving that using this reuse address socket option, or integrating a mechanism that shuts down the server gracefully, or killing the server not gracefully and checking which process is still attached to that port and killing that process also typically helps. And then everything is free again, or you wait until the operating system realizes, okay, this is a dead horse, I need to clean it up. Many ways possible. Something typically happening based on multiple network interfaces. This problem will arise when, or typically arises when you are trying to communicate with your project partner. So if you are capable of communicating on your server, on your system, you typically try to, let's try communicating with a different computer. And then sometimes you have the problem that one of you is working in a virtual machine and the virtual machine does not grant the access to the outside world, and switches something, changes something. And then you have to check if you're in the same network or if your IP address is commonly known, and then you might communicate with your project partner in a decent way. Another thing that tends to happen is a vanishing initial UDP package. This may happen when you try to communicate using UDP and you try to send multiple UDP packages. It can happen that the first UDP package hasn't left the communication thingy in the background and is overwritten by the following one. So, but this is typically something you have to consider when you use UDP. Based on protocols you have to use or implement or construct is the order of the packages, if it is necessary to have an order of packages, or the size of the content and stuff like that. But this is only relevant if you try to do some in-depth communication with the UDP approach. So it's 9:35. We can still, how much time? Let's make a break now. So we make a break till 9:40, and 9:40 we start with the rest of the stuff, checking quite fast with the protocols and then going to threading, because threading is important and we need to do threading today. Otherwise we are getting out of our timetable. Okay, so 5-minute break or 4-minute break now, and then we return to protocols. Okay, 9:40. Let's continue with protocols. So, as we already heard, protocols are important. Protocols are used everywhere. Sometimes we see the protocols, sometimes we don't. Protocols we don't see, for instance, and already used are the protocols the TCP version on UDP communication uses in the background in order to communicate in our exercise. But of course, even in our exercise, the system knows and uses a protocol to check if the data that has been integrated into the socket from us comes out in the right direction and in the right order and with the right amount on the other side. And in order to check that, it internally uses a protocol in order to make sure that all the bytes that came in come out on the other side. But we don't see that. It's hidden from us inside this communication layer. We just use it, or we just use it by accessing this communication layer through the socket API. And what we will then do is building on top of that later on in our exercise our own protocol. That is done by everyone else, as we will later see. So this building a protocol on top of other protocols is a common thing. And it is used all over the place in the system and in the internet and on our computers. So let's see. So the idea, of course, is we want to communicate and we want to exchange information through communication. And in order to do that, we need rules. So we all we currently use the English language to communicate with each other, and of course the English language, as every other language, has rules based on which words I'm allowed to use and in which order these words should be used. And this, of course, is rules stated as the grammar of the language. And funnily enough, the grammar of the natural languages is or can be defined similar to the languages as computer programming languages or protocols used in the machines. And that's quite funny because it's one of the few things I can talk to with my wife, which is on a totally different level of science, different corner of science, so more humanistics, and we realized that she uses Chomsky grammar and I use Chomsky grammar, and that was quite funny at that point in time. In the communication technology, these rules that make up the communication, that define how the communication should take place, what words are used, in which order these words are used, which signs are usable and what signs are not usable, this is called protocols. It's just a naming aspect for we define how the communication should take place and what is allowed and what is not. And of course, different organizations, companies do define these protocols. And if the protocols are defined by a global institution, by a standardization organization commonly known, then that is good, because then this protocol is typically open and we can use that, and we can use the knowledge about the protocol to communicate with a system that speaks this protocol. It gets more complicated when a specific company does its own protocol and hides the knowledge about this protocol and hides the rules. Then we typically speak about proprietary protocols. And this makes the life for us hard, because if we want to talk to a system that hides its protocol, we have the problem that we cannot speak with it. We don't know which word it uses, which language it uses, and therefore the knowledge about the protocol, about the interface, is that important to you. And of course, you can try to to extract the knowledge what language is used and how the language is structured, but this is a really piece of work. And therefore, proprietary protocols are always bad, open protocols are always good, because then we can just read it and then we know how it is structured and then we can use it and everything is fine. One of the most used protocols is where protocols are used is the ISO-OSI reference model, as you have seen in multiple lectures, I assume. And we are at this border here in our exercise. So at this point, we are in our exercise because we use the TCP, the communication layer, in order to send some data to a communication partner. Of course, we are in the application layer because we are building an application on top of that. But these layers that are depicted here are not relevant to us at this point in time. Well, that's basically the idea. And based on all this, on this reference model, all the different layers define their own protocols. And the idea is that everyone adds some knowledge to the real message that needs to be sent. So the idea is I have a program that wants to send data to a communication partner. So I have my data, which makes up this maximum or can be maximized to the point there where this maximum segment size is defined, as we talked about earlier on. And to this piece of data I want to communicate, every layer adds some data, and it adds as much data as it needs to later identify, okay, what data has been sent to me, from whom has the data been sent to me, is all the data that should have been sent available, is it in the right order? And so that is added on, and that's the reason why TCP is slower than UDP, because TCP needs to check order, has everything arrived? No, then reacquire, rechecked, and UDP just send data and hope for the best. And that's basically the idea. And every layer adds on its whatever it needs to decide what is necessary and if everything has gone right or wrong to this communication package. So starting from here, the package increases in size, and this is typically done. And if things are really complicated, you tend to stack these protocols. So you use a layered approach where every layer is responsible for a specific aspect of the rather complicated communication process. So you first check, so everyone is specialized on a specific task during this communication. And in order to do that, you can use a layered approach, which is quite common in computer science. And this is just the way we are currently doing it. We are building an application that uses, there's a typo in it, of course, it's UDP, not UPP. I have to correct that. I have to write that down because otherwise I will not find it again when this lecture is in the end. UPP. Okay. So I will check that later on. So it's UDP, of course, and we are building something like that. And as you can see, all the other communication forms are sitting on top of this UDP and TCP communication. So everything, when you open up a browser, in the background, sockets are used. And if you have an application that is checking your emails, sockets are used. If you are using your social media platform, TikTok or whatever, and Snapchat, and I don't know them all, then sockets are used. Always sockets are used. And that's the reason why we take a look at the sockets in our lecture. And every application defines its own protocol. So there are hundreds, thousands, millions of protocols that are using, that are defined and that are using TCP and UDP in order to communicate with distant computers. And we are trying to do the same, but on a very, very simple and abstract level, because building a protocol that is fully fledged and errorless or error-free, this takes up lots of time and lots of testing, and we don't have that much time. And yeah, therefore we will do a very simple one, and then everything goes as planned, hopefully. Yeah, layout protocols, I already said that when the system gets more and more complex, then it's quite useful to build for every complex aspect a specific layer that is responsible for that, and then solve the problem step by step. Again, this divide and conquer approach, which we typically use in computer science to get what we want, is we reduce complexity, split up everything into nice manageable segments, and then we communicate and then we solve the problem. And this also goes for protocols. If it's too complicated to go in one piece, then try to come up with a decent solution, and perhaps layering is the way you want to do and can do it. And this is, again, this showing you, okay, this is what we really want to communicate. And on top of that, different other payload header aspects are added by every layer. So we think we communicate only this, but in reality, we communicate way more data with every time we use a socket. But of course, this is all coded, optimized to the maximum, and typically the payload is so not optimized that it makes not really a difference to use all this header information. This is just piece of cake regarding using XML or JSON in here and the HTTP protocol, which is not optimized at all. And therefore, this doesn't really need to be taken into account, at least at our level of excellence. This brings us to a thing that gets important during your coding lifetime, using threads, integrating parallelism. This is really, really, really important, because every program, every project you will be working on will in some way use parallelism and using threads. And therefore you need to get as much practice with threads as possible. And that's also the reason why if you're somewhat trailing behind in the exercise, skip UDP, skip IP version 6, go right to the threads, because this is important, knowing how to play around with threads. And if you solve that, and then try around with synchronization, because this is equally that important, but makes your life even more complicated. So why do we need threads? What we already experienced is that when we use TCP/IP communication, we know that the server blocks in the accept method. We know that the receive method blocks, which of course means if we have a system that has a user interface and the flow of the processing of your programs is blocked in one of these communication methods, this of course means, if you don't have multiple threads, that you cannot interact with the user interface. So your application freezes. And you all know what happens if your application freezes. From a user perspective, the system doesn't work anymore, which of course is not exaggerated. If your program freezes, it's not working anymore. That it is still alive and waiting for an answer from a distant server cannot be known to the users, because you perhaps use a transparent approach and don't show the users that you're currently actively waiting. But of course, this is not a decent behavior of application, so you tend to split up the communication to a different thread, and then your user interface is still responsive. The problem is that you split up the communication in a different thread, and then of course, you have parallelism. And these things need to be brought into sync again. And bringing these pieces of code back into sync again is rather complicated, especially if you're just a programming beginner. Typically, then programming itself is already complicated, and now suddenly we have two command flows at the same time. You don't know in which segment the parallelized aspect currently is, and things get more complicated. So in order to support this concurrency, there are multiple ways to achieve something like that. We can use multiple processes, but processes are expensive, so we will use threading. We will use threading, and threads are defined in the literature as lightweighted processes, but they are of course not a process. They are entities that are living inside one process and use the resources of the process and the memory of the process. And the problem is the process is managed by the operating system. That the process cannot accidentally access the memory of something else and writing in some other one's memory, the operating system takes care. The problem with the threads is they are inside the process and they are not managed by the operating system. So this means the threading and the threads interacting with the memory inside the process, this is our responsibility. And this is where life gets complicated. And you will see that once you play around with threading and coroutines and stuff like that, then things get really nasty. So we virtually parallelize, and with our architecture, CPU architecture, we can not only virtually parallelize stuff, we can really parallelize stuff depending on how the threading mechanism is incorporated into the overall system and working on the machine. So we just first talk about virtual parallelism, where the different threads share the same processor. So one thing is done, the other one is internally the switch, the other thread is using the CPU, then the other one is using the CPU, and this is managed by the operating system and the system in the background. And therefore, this is not something that is relevant for us, at least if we're just reading data. And if one of these threads is blocked, then the other one gets the CPU and the other one is just waiting for getting whatever it needs to get. What are the advantages? So these are the advantages. We can integrate virtual or real parallelism. So building an application that supports communication with a distant server, with having a blocking receive method without slowing down the user interface, and everything is still working. The disadvantage is something I already told you, that the threads inside the processes are not secured against each other. So they use the same memory. And this really makes life complicated, because you as programmers are responsible of managing the access to the memory. And there can be many nasty problems waiting around the corner. And of course, concurrency multiplies complexity. Not only one control flow you have to keep in your mind and think about, and realizing, okay, now the program should be here, the value should be that. That would be nice. And if it's not nice, then I have to rethink. And now suddenly you have 3, 4, 5 of these threads doing stuff simultaneously. And then you have to think about that as well. So how do threads work? So the idea is we have our main thread, our main command loop, if you want to call it, command flow, not loop. So you start your program, and at some point in time, in your program you want to split up, create a new thread. So you call the create thread method, then internally a thread is created and the thread enters its thread method. And from this create to this entering of the thread method, suddenly two command flows are available in your system. And sometimes they share the same CPU, sometimes they are moved out outwards to different other kernels, kernel, and then you have real real parallelism. But we tend to think about, okay, they are sharing one CPU, so they are both running simultaneously, and the thread runs as long as it resides inside its thread method. So the thread is existing as long as the thread method is active, as long as the control flow is inside this method. Once it leaves it via return or exit, this thread is shut down. The problem is typically you need to clean up the mess afterwards, and you can use a join command in order for the main command to wait till the thread has been finished, and then you can clean up the mess and then continue with the main part. That totally depends on the, how your system should work. But that's something we take a look at later on. So how do we create a thread? So we will take a look at the create thread method. And depending on what system you are using, we have either pthread create. So this is for the Linux and iOS world and WinSock, not WinSock, Cygwin world. We use the pthread create method, which has this signature, or we have the create thread method that is on the Visual Studio side of the world. And this is responsible of creating a new thread, these two. And as you can see, pthread create thread, they are quite similar. And they also have quite similar properties. The create thread has a few more, and this one up here has a few less, but typically they are just the same, have the same idea. And they create a new thread, and inside this thread, the provided method is executed. And what you can see here is that you provide pointer to a function. So that is residing in the pthread create here. So you target a function that should be executed inside the thread. And in here, it's this parameter that is managed by the thread later on. What do we need in order to work with the create thread method? We need the thread ID. So this is in common with both of them. We have the thread ID here on top in the pthread and in the bottom here with the WinSock implementation. So we need, when we call something like that, the system will automatically integrate the ID of the thread into what we provide here. And we can later use the thread ID to reference the thread and shut it down, cancel it, and stuff like that. So this might become handy. We, in both versions, can set some so-called thread attributes, thread properties, which is something we don't do in this lecture. We need to provide the start routine. So what function should be executed in parallel to the main control flow. And we can provide some parameters to this start routine, which we also have to provide to the create thread method. And these are basically, these three are the main things we need to take care of. The ID is important to get a handle to the thread, to still have it under our control. The start routine pointing at the function that needs to be executed, and the parameters that we want to put into the start routine. And this is basically the main thing that is relevant for us. And depending on the system you're using, you have some additional parameters, like for instance, okay, for the thread, how large should the stack be? Or how the creation should take place. Return values, depending on what you're using, 0 and on the Unix world means it worked fine, or an error code is returned. And in the Windows world, new null is returned, or reference to the new thread handle is returned. And so you have to decide which world you are currently working on, and then you can use that. So this brings us into the how to really do it. So we need to call the create thread method somewhat after the accept method in our exercise. So we accept in a socket, and then we send the send and receive tuple that manages the communication with the client into a separate thread. So that's the basic idea. And after we split up the communication with the client into a separate thread, the main UI thread, the main thread, returns to the accept method where it blocks, and the communication is inside the spawned thread. And so inside this spawned thread, the server is waiting in the receive method from a command or from an information from the client. And when it receives that, it sends its reply and then waits for the next communication with the client until the client decides, okay, now I want to shut down the communication. And then the client, the spawned thread is discarded. And that's basically the idea.
Sure, question.
Yeah, question.
Are there any discrepancies concerning the slides? Because when you showed the spawning of the new thread, this slide was already missing. Now there's some comments missing.
Okay, that could be the case, because as I said, I'm always updating the slides and the exercises, and maybe I forgot to upload that last year. Let me correct that. So I need this, I need slides. So let's check. I did that yesterday, but that was just a minor aspect. Export, PDF, generate that. And we are in 3, publish, yes. Then I need my Moodle stuff, go to the own ideas, so it's still publishing. So once it's published that, we can upload that on the e-learning platform. So let's step through that. Bind method, socket options, struct, encapsulate, cleanup, concurrency, critical section, semaphores. I think we can get rid of that one. So these are just commentaries for me to work on that. So we save this and we save that and we move that over here and we override that and save that. And once it's completed saving that, you should be able to get a new version of the slides from the e-learning platform. The problem will be if you just press download again, the caching will of your browser will provide you with the wrong version. So you have to clean up the cache of your browser or restrict that by pressing Control Shift and then pressing the link, something like that. And then you should have the current version of the slides. Yeah, already there. Nice. Sorry. As soon as you realize that I'm using a different version, and this will happen next year next semester when we together again, at least with the mobile computing students, you just have to remind me that I forgot that. And this is important that you tell me that. So now I just need das Tool. Jetzt kriege ich diesen dämlichen Laserpointer nicht in die Hände, weil die dämliche Taskbar offen ist. Kriege ich die schon noch? Da. Okay, so this brings us how to implement that later on. So I already told you that after accept, the idea in the exercise is to spawn this receive, send, respectively send and receive communication into a separate thread. Of course, we only need a separate thread on the server side, not on the client side. So in the client side, we keep it simple. We don't need a class on the client side as well. We just need classes on the server side. And in order to spawn a thread, we call this thread create method. And as you can see, we provide a thread ID, which is of type pthread_t, and on the Windows world, something slightly different. We provide the reference to the ID. We don't give any options or properties for the for the thread construction. This is the name of the function we want to be parallelized, to be running inside the spawn thread. And we want to provide some parameters to this line communication. And therefore, the parameters are provided. Something you need to take into account is this nice little AND symbol here. If you have parameters on the stack, you need the AND symbol. If you provide the parameters on the heap, of course, you don't, or you have to discard of the AND symbol. Otherwise, bad things will happen. So keep that in mind. If you are keeping parameter on the stack, you need a reference to that. And if you don't, if you have a pointer to the parameters, you don't need the reference symbol. This is something that went bad last time in the exercise. So I marked it specifically. So we know how to spawn a thread. Now, the next important thing is, how does this method we can target and we can spawn into this thread need to look like? This is the next important step. So the thread target method signature needs to be defined. And this method contains the code that is parallelized. And the thread is running as long as the control flow is inside this method. So typically the thread method has the first thing that happens is while alive, do something. And while alive means this thread method is running for quite a few cycles until the client tells the server, I want to quit. Then alive is set to false, and then the client leaves its queue, runs to the end of the thread method, leaves the thread method, then the system can start cleaning up the mess afterwards. That's basically what is necessary. So what is to be said about the signature of the thread target method? The return value. Well, let's start the other way around. The thread method needs to have a very, very specific signature. It needs to look exactly as stated. Otherwise, it will not work. There is no room, no margin for error. You need to specify it exactly. You can decide upon the name, and you can decide upon the name of the parameters, but that's basically it. The signature is predefined. No way to leave that. So the signature slightly differs depending on the system you're using. In iOS and Linux, it's void pointer return value. And in the Windows world, it's int return value. It has a single void star method parameter. So again, lots of void stars, which is your alarm should be sounding big time. if void pointers are involved. Yeah, but that's basically it. And the thread method needs to be static. If it's not static, it won't work. This is one of the few methods that need to be static. And try to keep the static to the thread method and not extend it to anything else. What I mean by that, you will realize later when you're trying to communicate with the server and stuff that is inside the server. But you will see that once you're there. So inside the H file, you have something like static void pointer, the name you want to choose. I've chosen client communication, and the parameter is void star and a single parameter, not two parameters. One single parameter can be passed to this method, not more. And of course, you ask yourself now, if you think about it, one parameter, is one parameter really enough? What if I have multiple things I want to tell this thread method needs to take into account and needs to work on? How can I stuff multiple things inside this void star parameter? And the good thing, of course, is this void star parameter, void star can be anything. Void star means there is no limit. And of course, you can just define a class that goes into this void star parameter and then unpack this, this class later on. And inside this class, anything can be defined you want to work with. And of course, in the C++ world, we don't need a fully fledged class. We just use a struct. So we define a struct that contains everything we want to use inside this thread method. And in our exercise, we will definitely need the socket handle that gives us access to our communication partner, perhaps the address, or later on, perhaps a reference to the server itself in order to communicate with something that resides inside the server. Remarks here, careful where you put this socket parameter, on the heap or the stack, because when you support multiple clients at the same time, then of course you generate and you have the parameters on the stack. Then of course these values are overwritten the moment a new client connects to this server. Then the socket handle is a different socket handle. And if you have that on the stack, then perhaps in the other parallelized spawned thread, these values also change if you don't copy them. And therefore, yeah, this brings us to the next problems that arises when we do integrate parallelism. But this may sound like, okay, I will never use parallelism, but then you will be never able to write an application that can be called something like an application. So every big system, every system that communicates with the outside world needs parallelism. There is no way around it. Okay, so how to encapsulate parameters inside the system. So this is an example that uses the heap version. So we have socket parameters. We generate a new object of the socket parameters. We attach the client socket and the client address to the socket parameters. Then we use the create thread version of the WinSock library. So we have client communication here. We put the parameters inside here. And then everything goes as planned. And another typo is available. So slide 550. Does anyone see the typo in the slide? Anyone realizing? So this is the method name we want to target. And inside the server, we define this method. So inside the CPP file, the static is dropped, but in the H file, the static is still available. Otherwise, the signature of the method is the same. And then we can use this parameter that comes in here, cast it to whatever we threw in right here. So we can cast the object to the real class. And of course, this is the dangerous situation because it's void star. We don't know what this really is. We just assume that it is what we put inside. And as long as we are under control and we know that these two, this and this is the same, everything is fine. If these two are not the same because we are doing it on different versions, for instance, then everything goes south from this line of code. And afterwards, if everything works well, we can access the client socket, we can access the client address, we can access the reference to the server. And then inside our Spawn thread, we can use that to send and receive data as much as we want. And when you have integrated these aspects into your code, your server will be capable of communicating with dozens of clients at the same time. And that's just a nice thing because every server is typically available or capable of communicating with different clients at the same time. Some general remarks when we use threads. One of the primary remarks is fairness. So even if you're using multi-threaded approaches, you can build a system that degenerates or drags down the complete application into not unusability, because when you do some really intensive calculation inside the thread, it tends to grab as much CPU time as possible. And grabbing as much CPU time as possible means that the CPU time for the other aspects of your program is reduced. And typically you don't want that. So one thing you can do is prioritize it, of course. Or you can, and which is also typically done, is you can integrate fairness into this thread method. That means that typically when you do some calculation, you have cycles. So calculate this, calculate that, and you go through a queue. And what you can do is after each of these walkthroughs, you can tell the thread method to sleep for a millisecond or for a nanosecond. So that the mechanism that is working in the background that is sharing the CPU realizes, okay, this one goes to sleep now, and I can give the CPU to a different thread, to a different process. And this brings in again a useful timing into your whole application. You can either use sleep, where you can say, okay, sleep for a second, sleep for a millisecond, or you can use the method yield, which is undefined in time. Just stop using the CPU, and then if yield is done, then it depends on how the background is organized. Adding on that, if you're using Unix, we have so-called attached or detached threads. And there are two versions of them. The attached threads are the default versions, and attached threads need to be cleaned up by us, programmers. So if you're using attached threads, you need to clean up the mess afterwards if you want to do it right. Inside our exercise, we may produce memory leaks. We may not clean up 100% after ourselves. But if you wanted to do it in a company and really earn money with it, you need to clean up. So we need to call the join, make a join call and catch everything and join the Spawn thread again with the main UI thread, may I call it this way. But you can also generate detached threads that are not necessarily needed to be joined. Aside, detached threads cannot be joined anymore, and detached threads are cleaned up by the system on its own. And what you can also do is use something like that is called cleanup, pthread cleanup, where you can call, it's something like the destructor of a thread, for instance. And there you can, if you allocated some memory on the heap inside the thread, you can use the pthread cleanup in order to, clean the heap and then die and shut down gracefully with the thread. Exactly. And on Windows, you have to close the thread handle, and of course you can join that also. Something in addition, and then I'm realizing that our time has run out, is that if you are using multiple threads in the company and stuff like that, you have to make sure that all the elements you're using inside the spawn thread method are multi-thread safe. And if they are not multi-thread safe, you have to make sure have to organize the synchronization, which is another thing we talk about next time we meet, because this also needs to be talked about. So if you're using multi-thread safe stuff, you get rid of some of the workload that waits for you when you use multi-threading. And of course, the documentation states if something is multi-thread safe or not. And if it's not stated, it's not multi-thread safe. It's explicitly told that this class is multi-thread safe. This queue is multi-thread safe. And of course, in our exercise, the queue we are using, the simple vector, is not multi-thread safe. So lots of stuff we need to take care of. Yeah, before we stop with the lecture, some aspects we can talk about, just show you. So there is a pthread join method that we can use, a pthread detach method, which we can use. These are all aspects that are optional, so we don't need to walk through in detail. But if you do the optional part, you definitely should take a look at these slides. Cleanup, as I said, calling the destructor if we want to. So small example. The close handle is, of course, the WinSock world again, and WinThread world, and wait for single object. Also, if you're using Visual Studio, wait for multiple object, use Visual Studio. And then the next thing, and this is what we talk about next time we meet again on Monday, is concurrency and synchronization. But we will just take the general introduction in depth, and then we continue with the Java side, and the rest, the synchronization mechanisms, is the optional part, and therefore we just skip through those in a quite fast manner. Okay, sorry for the extension of the lecture. So this was it for today in distributed information systems. As always, I will close down this channel in a minute or two and open up the group channel for the exercises. If you have any questions, contact me in the exercise or contact Mr. Plattner in the exercise. And if you're not sure, of course, automotive computing, you can also contact me, no problem at all. So lecture is closed. Have a nice one. We see each other in the exercises, and hopefully you can solve the exercise in time. Have a nice one. Bye.
Bye.
Goodbye.
Bye. Bye. So, machen wir das mal dicht. Das kommt da und das kommt da.